Well, hi, welcome. I'm Blasty, and today we'll be talking about runtime backdooring for loss and profit, because I needed a funny subtitle. So first of all, who am I? Well, I'm Blasty. I'm a hacker, troll, geek, whatever you want to call it. Most of all, I'm forever alone. And being forever alone gives me the benefit that I have a lot of free time to spare on useless, silly, or otherwise useful stuff. Well, I'm also part of Team Tweezers, Titan, Vel Overflow, Eindbazen, a couple of internet groupies, but we won't be discussing that right now because it's boring. Okay, so first of all, some abstracts from my talk, what we will be discussing today. So first of all, I'll give you a short introduction to runtime debugging, what is runtime debugging, etc. Next of all, we need some victim to actually apply runtime debugging. We'll talk about binary signature matching, binary patching, complicated stuff, we'll get to that. Finally we will talk about putting it all together. So I've made an actual product that you can clone from GitHub after the end of this presentation. And we'll do a short live demo. So first of all, small disclaimer. Last year I had some small complaints about the intent and the way I think about things. So I thought I'd put this little slide in here to make up for that. Everything presented here is meant for educational and recreational purposes only. So that means if I say like, well, we're going to log into this FBI box now, I'm probably kidding, and I'm not insisting that you should actually break into FBI machines or whatever. Right. A joke is a joke, and I joke a lot, so yeah, get used to it, I guess. Last of all, we are here to discuss technology and not ethics.
Not an ethical hacker.
So, another filler slide here. Some apologies from me. This can be quite techy stuff. I might be jumping back and forth a bit. It's all about gritty, nitty details, and an hour is just not enough to cover all of it. So I might be glancing over some details. Some stuff might be in a weird order, but source code will be available after the talk. So whatever you don't understand now, you can always look at the source code later and contact me if you have any questions. So, runtime backdooring. What is runtime backdooring? Let's create a situation here. So you're a lead hacker, right? Everybody's a lead hacker here, right? Who's a lead hacker? Come on, show us your hands. No lead hackers?
Come on, Bertie. Come on.
So say you want to attack me, the great Blasty. I have my own private cloud, of course, because I like to, consolidate and isolate my services. If one machine gets compromised, I don't want another machine to get compromised. Stuff like that. In fact, I don't, but let's pretend I do for today. So my cloud consists of 3 machines. An IRC box. This is also where I store all my 0 days, of course, because you shit where you eat, right? I have a web server box and an X11 box, because old school like that, they use X11 and then, use to render my Firefox and terminal windows and stuff. So, one boring afternoon on IRC, I accidentally, this is very unfortunate, but I accidentally paste one of my passwords into the IRC. And I go like, oops! But before you know it, some lead hacker, has picked up on that. Hey, that's a weird looking string, that might be one of his passwords. So the lead hacker quickly tries to connect to any of the machines in my cloud using SSH in my username. Eventually he manages to get the shell using that password. And coincidentally he has broken into the X11 box. So this is where I run my X applications. He's like, well, that's interesting, but I would like to take it a step further, compromise the entire cloud infrastructure Blasty has going. So it's like, okay, let's have a look at the process list. So he does PSX to give all the processes of the current user. And he notices in there, I'm actually logged in right now, and I'm using an external terminal emulator. This is like a little terminal client where you punch commands in. So, attacker proceeds to download this evil backdoor to my machine. And what this evil backdoor does is, it gives us a process ID and a path to a log file. And what it will do, it will attach to the running extern process, so without terminating it, it will attach to it, like a debugger would. It injects some evil code, it patches some code, and the end result is that everything I now type in my extern will also get keylogged to a file. So the hacker is tailing the file here, and he sees I'm like becoming root on my own machine because I need to tweak some X11 server configuration or whatever, and he sees my positive I love donkeys, and well, he taps out of that, and then he sudos the root, and well, he has root on my machine. This is pretty bad. But this is just an example to illustrate what runtime backdooring could do and how it's useful. It's a way to inject code into a running process without actually touching the binary of that program on disk. So it's stealth in the sense that if someone were to do like tripwire or whatever, does MD5 or SHA-1 checksums of his files on the disk, he would notice that one of his programs actually got infected because it got infected in memory. So the copy on disk is still virgin. Let's talk about debugging or debuggers. Who in here doesn't know what a debugger is? Correct. That does speed things up for me. Well, so basically a debugger is a way to have a look into a program or a kernel that is running. So you somehow trap the program or the kernel and you get into the debugger and you have all kinds of low-level information. You can see which instructions it's currently executing. You can have a look into memory. You can see what registers are in use. The screenshot I have here is some Solaris kernel debugger, but look fancy enough. So I thought, hey, that's good. So, debuggers on Linux x86 64-bit. Well, there's GDB, and then there's GDB. And does anyone know any like really widespread debuggers that are actually in use outside of GDB on Linux x86? Me neither. So there's GDB, and then there's toy debuggers. And basically what we will be building here today is some kind of toy debugger. So a program that uses a certain API and implements specific stuff like a debugger would. How is this done? How does the debugger work? On Linux there's the ptrace interface for debugging. So there's a system call exposed by the kernel that a userland program can use to attach to any process it has enough privileges to. So say I'm running as user blasty, I can attach to any of my own processes. But if I were running as root, I could of course attach to any process. And it's pretty much the one and only debugging interface that allows a userland application to attach to another userland application and do funny shit. So, ptrace has a bunch of primitives. I call those the 7 primitives to rule the world. It's not exactly true because there's more than 7 primitives in ptrace, but these are the ones you will be using most. So we have ptrace attach. This allows us to attach to a running process. We give it a process ID and it can attach to it. Then we have detach. Of course, when we're done infecting a process, we want to nicely clean up and detach from the program again. Then we have ptrace get recs or get registers. What this does is gets the current CPU context, including all the registers, and returns it as a nice structure to the application. Then we have ptrace set recs or set registers to change registers of a running program. Then we have ptrace peek text and ptrace poke text. Well, as you all probably know, peek and poke, maybe some of you have had a Commodore 64 back then and are used to typing those sequences. But peeking is basically having a look into memory, and poking is basically putting something new into memory or changing something in memory. And then we have ptrace single step. Ptrace single step is useful to have a program execute a single instruction and then halt again. So let's talk about injecting system calls. Why is injecting system calls useful? Well, we can make a running program do all kinds of stuff, and then after injecting the system call, we can make it resume execution. So what do we do to inject the system call? First, well, we hold the process. We execute a ptrace get recs to get the current CPU context. We back up this CPU context so we can restore it later. Now in this CPU context, we change a couple of registers. We point the RIP, the instruction pointer, to some location that has a syscall instruction. So any program will probably have some byte sequence in an executable region that is a syscall instruction. So we point the instruction pointer to one of those. And then we set up the ROX register with the syscall number you want to invoke, and well, the parameters for a syscall are supplied as to the usual syscall calling convention on Linux x86, 64-bit. Then we set these new registers using setrex, so the modified CPU context is put into the process, and then we instruct the process to execute a single instruction. So right now it will execute the syscall instruction because we set the instruction pointer to an address which has a syscall instruction. So after the single instruction has been executed and the kernel has done its stuff, because syscall is a single instruction in userland, syscall will be executed, and using setrex we can restore original CPU context, and we can continue the process like it would normally. And at this point we have successfully injected a syscall. This, I will explain later why this is useful and what we are going to use this for. So let's talk about a victim. I was like, okay, all this is cool, I can attach to processes, I can do stuff in memory, I wrote some test programs. I'm like, yeah, it's cool, I can attack my own software, but that's no fun, right? We want a real victim. So I was like, yeah, let's go with OpenSSH. I think OpenSSH is pretty popular. Anyone in here use OpenSSH? Raise your hands, please. I don't want to.
I hope you're using at least OpenSSH and tell that.
But you can see there in the bottom is actually a scene from the Matrix Reloaded, I think, where Trinity logs into it and she executes some SSH exploit or whatever. I thought it would be funny to include. Carrying on. So OpenSSH is the perfect victim. Pretty much every Unix box has OpenSSH for administrative purposes, whatever. It's a remotely exposed service that provides us with a free cryptography layer. So if we were to hook into Telnet, for example, and I want all my secret stuff to be encrypted, I'd have to implement encryption myself. But OpenSSH comes with free encryption out of the box that we can piggyback on. And well, the code base for OpenSSH is surprisingly clean for something written by a bunch of LSD acid-dropping hippies. I mean, really, I've spent like maybe 2 weeks reading through pretty much the entire OpenSSH source code just to familiarize myself with how things are structured and laid out there. And well, you know, I needed this knowledge to actually write a usable backdoor for OpenSSH, because you can write a usable backdoor without knowing the code base you're attacking. So I spent like, I don't know, 2 weeks on and off, an hour here, an hour there, reading OpenSSH code, and I was like, hey, this is actually pretty good software engineering they did here. I would implement it like this if I had to do it myself. Too bad I don't do any big programming projects, that's not really my thing. So you want to design a patch. Well, I thought some people have attacked OpenSSH in the past using runtime infection, and they would always do stuff like they inject some routine that hooks into the password-based authentication, and then they have some magic password, and you can log in as any user using that magic password. And okay, that's cool, but we can like kick it up a notch. I mean, everyone pretty much knows about public key encryption, I assume, or authentication for OpenSSH. So I thought, wouldn't it be fun if we can inject our own public key into a running OpenSSH process? And so like, normally OpenSSH will check your authorized keys file to see if a public key is in there, and if it matches, then you get authenticated. But of course we don't want to touch the authorized keys file on the machine that we hacked, because well, it leaves a trace on the disk, and that's bad. So what we're going to do is we're going to inject our own public key into a running SSH process. We're going to redirect some of the code in there, so it actually checks for a secret public key. And if it matches, then it will drop us into a shell, regardless of which user you're trying to authenticate as, and regardless of whether the user has an authorized key swap or not. So this was pretty hair-pulling process to get right. So there's out2pubkey.c, which implements the public key authentication mechanism. And then in there you have a user key allowed routine, which is basically what we want to attack. But then there's some indirection. User key allowed calls user key allowed 2, and then user key allowed 2, there's some more indirection, and eventually it comes to a key equal call, and that's the decision maker, which returns whether integer 1 for authentication successful or integer 0 for failure. Okay, my head hurts now. So I set out and started to design a patch. I was like, okay, we can just grab the OpenSSH tarball from, well, their website, and then, well, I was reading the C code anyway, so I thought, first let me try to implement this backdoor in C. So I just took the OpenSSH code, added my own routine, and patched a bunch of places where it calls the user key allowed 2 with my user key backdoor 2, which eventually at the end invokes the real user key allowed 2 again. So original functionality and authentication will still work and should go unnoticed. So what we see here is I have a string copy call to my backdoor key with a static backdoor key in there. That's not really optimal. And while I hacked this directly into the OpenSSH code, recompiled OpenSSH, took some fiddling, but I got it to work. I'm like, okay, that's nice. So we have a modified OpenSSH daemon binary now that we could deploy to some box. But again, we're touching the disk. We don't want to touch the disk because that means evidence, and evidence means getting caught. But there are some troubles in 2012 with process infection. I mean, people have done quite some research on process infection in the past. There's nice articles in Prac that I definitely recommend reading on the subject. But one, they focus on 32-bit Linux. And second of all, they were written a couple of years ago when a lot of mitigation mechanisms weren't in place yet. So I thought, well, Ubuntu is a pretty common distribution for Linux. A lot of people use it in the server world as well these days, so people moving away from Debian because the update schedule is too slow or whatever. I thought Ubuntu would be a pretty good benchmark to make my tool to work with. Ubuntu is pretty serious about security, by the way. They have a nice wiki with a matrix where they show which security features they implement, and they, well, yeah, it's pretty good, I have to say. So, on Ubuntu, SSH daemon ships as a PI executable. What does this mean? PI stands for position independent code, position independent executable actually. So what this means is that the compiler generates and links a binary that you can basically put anywhere in memory and it would still run fine. With a non-PI binary, it needs to be loaded at a specific load address, or otherwise certain hard-coded pointers and stuff will not match up with the actual image in memory. But they compile it as position independent executable, so this means they can have SSHD anywhere in memory. Of course, this poses a few problems for us because we need to know a lot of pointers to do patching and stuff, and if they change all the time, well, we need to determine them at runtime. And then there's the second challenge, that is whenever SSHD forks or clones its process image, it nowadays also does an execve call to actually re-execute the binary in a new process. What this means is that it loads the SSHD binary from disk and loads that into the process memory. This is bad because our patches live in memory. We're going to patch the parent and we don't want the patch to get overwritten once it re-executes itself. So let's talk a bit more about re-execution. So like I just said, every new SSH connection gets cloned into a separate process image. This is not really an issue, but nowadays they also execve themselves again. So we get a completely clean process image and our patches will be gone. Address space and randomization will be reinitialized, so there will be different memory mappings for a child. And well, it's a big headache, right? So So this is also the reason you need to execute SSHD using its full absolute path, because otherwise, once it gets to re-execute itself, it doesn't know where to find itself. So if you have the exact VE call, the first argument will be user sbin SSHD rather than SSHD or whatever. So let's look a bit at how re-execution is implemented. So the funny thing is, there actually is a hidden configuration or command line option in OpenSSH to turn re-execution off. If you look in the manual pages of OpenSSH, you won't find any mention of this, this toggle, which I found pretty funny. I mean, why is it there? So further on, it checks whether the re-execute flag is set, and then it actually does the re-execute and ends with an exit VE call, which gives us a lot of trouble. So I thought, hey, what if we just start OpenSSH with -R? And indeed, it turned off re-execution and patching was reliable again. But this is a problem, because if we want to run SSH with -R, this is not a default. So it means we need to either stop the SSH daemon and restart it with -R. You probably want to modify the init script for that or something. And well, it's pretty visible. You don't want to stop SSH daemon. You want to stay stealth. Then we have stripped binaries. Ubuntu likes to strip a lot of important binaries to make my life a lot harder. So what does stripping mean? Executable has symbols, which are, well, when you're coding, you write function names, you like function do this and do that. Those are basically symbols. This is information the compiler retains when compiling and linking your binary. So when you attach a debugger, the debugger knows that it's inside function do this or do that. So symbols are very convenient for debugging, but for a release or production binary, they aren't often needed. So they strip them out, you get a smaller executable, maybe some more performance, I don't know, I don't think so. But yeah, we can't use these symbols during runtime to look up functions in SSHD, because Ubuntu stripped them for us, so we can rely on that. So I thought, well, we have to find a solution for this. And I was reading through OpenSSH codes, hours and hours, nights and nights, more coffee and coffee. And I finally was like, hey, wait a second. So a lot of OpenSSH routines have debug statements like this one here. Well, what is a debug statement? Basically, it means if you're running OpenSSH in a very verbose or with a high log level mode, it will log these messages to syslog or whatever. But that's not of interest to us, because usually the log level is low and well, it's not that important. The important part is that they're using a constant string here. In this case, it's out2_challenge yada yada yada. So incidentally, the function is also called out2challenge. So basically what we can do, we can look for these strings, and this string is exclusively used in this function, and also has a function name at the start. So we can find references to these strings in the code, and from there backtrace to the entry point of the routine to find the address of the function. So for this function, we would look for the string out2challenge :user blah inside of memory. Let's look at a bit of assembly code for this. So we have the same routine here as we had here in assembly. So this is like a function prologue, it does some yada yada yada. And at this point it loads a pointer to the out2challenge string. So whenever it's going to invoke the debug function, it will load the register RDI with a pointer to that string. So what we can do now is we can search for this string in memory, then we know where that string lives. Then we search the entire executable region of memory for a certain opcode pattern that loads that pointer into RDI. So if you look at the hex in the lower left corner, that's basically the load effective address instruction we see with the arrow there. So the left part, 48AD3D, indicates that it's a load effective address instruction, and the destination operand is the RDI register. And then it's followed by 4 bytes which are the offset. The offset is calculated relative to the instruction. So we have this load effective address instruction which lives at 20B17. Then we have the offset from that instruction, which is, well, it's little endian, so it's byte swap, so it's 03F932. So we add that together. Then we add another 7, because the total size of the instruction is 7. And we get this address, 60450. And if we look at that address, indeed, there is the string. It's cut off from the slide, but it's the string that is there. It's located at the memory address. So effectively, if we know where this string lives in memory, we can, for every position in the code, we can calculate an opcode and see if that opcode is present, which would load a pointer to that string in memory. I know, it sounds already complicated, but it isn't. So what we do, we find the string in memory, we find code referencing a pointer to the string, and from that instruction, from the load effective address instruction, we backtrace a couple instructions back to the routine prologue. Well, the prologue is basically the start of a function, so that's what we need. But I won't really go into the backtracing now. I basically do it by some certain signature binding, but it might be a bit complicated to cover here. And well, eventually we'll get the address of the function we're looking for, without having to rely on symbol lookup tables or other cheesy stuff. So let's talk about address space randomization a bit more. On Linux you have this usable proc file system thingy, which has a lot of information leaks usable for hackers, or otherwise diagnostic information. So what we do, say we work into this machine, right? This is my desktop at home actually, and we're root on this machine, and we're like, okay, let's have a look at the SSH daemon memory map. So we do a PS and we grep for SSHD, and we find that the SSHD process is using PID 2198. Then we look into the proc file system to get the complete memory map. I've actually truncated the memory map a bit, because SSHD likes to load a lot of external libraries. That's actually at least what it goes like this. But yeah, this is the important part. So here we can see that there's 3 regions for the SSHD binary. On the left, the first rectangle, we see the loading address for this. So the first address is the start address and the second is the end. Then we have another rectangle, and which is a permission mask for the pages. So you can have pages that are readable, writable, executable. I don't know what the P stands for actually, maybe someone will say. No. But the important parts here are the load address and the permission mask. So judging by the permission mask, we know which pages are executable. So if we are looking to reuse code, we will only scan executable pages because saves time. And we need the load address to defeat the address space randomization, because using this we can derive the base address and then we can just add static offsets to that, and all will be fine and dandy. So let's talk a bit about binary patching. So if I write a little hook for OpenSSH, like I did with this C code, it uses functions from OpenSSH itself. These functions, well, we don't know where they are, but we invented the symbol by debug string method for this, so we can backtrace them. But our hooking code also uses these functions, so it has function pointers to all these OpenSSH routines. But they change all the time because we do, well, runtime identification of routines, so it will work on multiple versions of OpenSSH. We have address space randomization, which changes the base address all the time. So what I did is, let's see, don't have it here. Basically in my code I write all my hooks in assembly, because you know I like assembly. You could probably do it in C, but it would take some fiddling to get it to a compiler to produce the right code. But I wrote all my hooks in assembly, and for every function pointer I'm calling into, I simply have a placeholder which is like 1111, 2222, and then during runtime I resolve all the function addresses using the previously discussed technique. And then I patch the placeholders to be the actual function addresses, and then we can show it into memory and have some fun. So, we talked about syscall injection previously. Now we're actually going to need it, because we need some place in memory where we can store our code. Of course we could, well, you know, pick some existing memory mapping that has some free or unused space, or dev code that is never actually called, and override that with our own code. But it would be no fun. We want something cleaner. We want to actually map a new memory page inside the existing process, and then we have a safe location for putting our code. So this is where the mmap syscall comes in the story. Using mmap, you can basically, well, you can create a new memory mapping, dynamically allocate some memory inside the process. What we do here, I have on the left you see the prototype for the mmap function, and on the right we see an example of how you would invoke it. So in this case we're going to try and map a page at offset lead boop 000. We have a size of 4K or whatever it is. We give some protection flags which say this page is readable, writable and executable, which is convenient. We say we want an anonymous shared mapping that is at a fixed address. Fixed is the most important part, because it means that mmap will actually try to do its best to give us a mapping at this exact address, which makes things easier. So this is what I was talking about previously. I have these placeholders in my assembly code. So I have like 111, 2222, and this is actually the key read function which should be called there. And then during runtime, when I've resolved all the function addresses, I patch this code. I just look for 111, 2222 to put the actual function pointer address there. Same goes for all the other calls. So let's start summing this up. We can determine the SSHD memory map by looking at the proc PID maps file. Then we look for a 0f05 code sequence, which is a syscall instruction, which we need for syscall injection. Of course, we could also, I don't know, patch one into memory somewhere and then jump to that, but I actually scan for a valid syscall instruction. Then we do a lookup of the rexec flag through the dynsim table. This is actually one of the few places where symbol resolution still works, because there are still symbols for some static variables, like this rexec flag, which we want to patch to prevent SSHD from re-executing itself and destroying our patches. So we patch this flag to 0 to prevent SSHD from re-executing. Then we locate the key allowed, key new, key read, key equal, key free, and restore UID, because all these functions are used inside my hook to do a clean initialization and clean up before returning to the original code, using the debug string to symbol technique. We patch all the placeholders in the hook code using the correct function pointers we just determined in the step above. Then we find a nice hole in the memory map close to the text section. It's kind of important to have it close, because we're relying on 32 bits offset, so if the distance is too big, then it won't be possible to patch it cleanly. And next we inject mmap syscall to allocate a fresh page where we can actually store our code. We find the call to key allowed, which is where we're going to patch. This is well, a call instruction, so it starts with E8 and then an offset. I think it's absolute, relative, I don't remember, I think it's relative. So we patch that to jump to our newly allocated page instead of the regular location. And of course, in the code that we shove into the new page, at the end we jump back to the original key allowed, so it still works. And if everything went fine, well, there will be profit for everyone. So, it's time for a live demo, I guess. I had a different placeholder image here.
Yeah, man, what the fuck? Why not?
So let's see. Okay, so this is is a super secret machine and we just hacked into using undisclosed techniques, maybe an exploit, configuration error, whatever, doesn't really matter. So we've broken into this machine and we want to like somewhat not persistently backdoor it. We want to backdoor it, but in a way that's stealth, right? So here I have another shell. This is actually my local computer. Of course I have a SSH key here. This is my SSH key. You see it has a nice signature and which has an evil hacker on some box. So we go to the machine we compromised. Just to make sure that there's no actual .sh folder here, no authorized keys file, no nothing. So we carefully in temp hux, some secret directory which has an injection utility. So now we look for the OpenSSH process. And we can see it's running with process ID 8345. So we just inject. And inject says, give me a process ID and a public key. So we say 8345, and say this, and then we say up. So we can see a bunch of stuff happening here. Well, it attaches to the process. It parses the memory map using proc-bit maps. It locates the base of the ELF executable in memory. It caches all these mappings to do some quick lookups. Finds a valid syscall instruction, which we can use for syscall injection. Finds the address of the rexec flag, fetches the rexec flag. Then it starts scanning for those routines using the symbol to debug string method. And you can see, well, key allowed is found at this address, key new is found at that address. And then it says in my evil binary at offset 97, it finds 77 and 78 and it matches it with that address. So the code will actually be correct once put into memory. It finds a bunch of more stuff. Eventually it goes looking for a nice hole in memory where it can map the page. It maps the page, it copies the evil Trojan into the new page, and then finally it patches the call in OpenSSH to user key allowed to invoke my secret backdoor first, which at the end will invoke the original function first again, and then it detaches and it's done. If everything went right, we can, let's see, what's the name of the machine? So as you can see, we have injected a backdoor into a running SSH daemon in a somewhat stealthy way. I mean, it's not completely stealth. I can talk about all the shortcomings of my implementation. For example, if we look at so let's look at the process map for you can actually see there's a page somewhere, it's not this one, but it says deleted as well, and that's my freshly mapped page. So actually by looking at the maps output, you could know that I injected a new page into memory. But of course there's ways around this by patching into existing memory mapping, so you don't create a new mapping. Apart from that, I haven't heard of anyone who actually has a way to verify memory mappings or know what is a legit memory mapping or not. So it's still pretty stealth. Let's see. Of course, all this code needs to be free and public for everyone to learn and earn. I don't know. There's a GitHub page, repository, shrape.git. The repository is there. I haven't actually pushed it yet. I will do it after the talk because it is an exclusive release for hacking a random 2600NL database. Call this, well, I needed a name for this, right? And this morning I settled with SSH rape. But previously to that we were joking around in RC, like, Would it be cool if we call it Fox Kit or something? Actually, the colors are a bit lost here, but I got some anonymous logo submissions from people who don't want to be publicly named here.
I like the smoky.
There are some similarities in there. One says Fox Kit, the other says Fuck It, and then there's another one that says Fox Kids. But too bad they didn't make it. It's exaggerated. It is. So, thanks for watching. That's about it. If there's any questions before we move on with questions, I would like this moment to give a free plug to the guys at CertifiedSecure.com. A lot of times people ask me, okay, all this hacking stuff is so cool, but where do I learn it? I mean, I've heard of SQL injections, but is there some place I can actually practice my SQL injections or path reversal attacks without making anyone pissed? I'm like, sure, CertifiedSecure.com. Check the place out, it's really cool. Alright, questions?
Do you also have a challenge for this one, or?
A challenge?
At Certified Secure?
No,
Oh,
not yet.
The
okay.
challenge is to patch their SSHD.
Okay.
No questions?
Get root first.
Okay. Blasty, thank you very much.